condition would be a co-Büchi acceptance that states that a state, in this case the state 1, should be seen at most finitely often in a run for this run to be accepting. To get smaller automata, we use the quite common strategy on using acceptance conditions that talk about transitions instead of states. So we shift the labels from the states to the transitions, and in most cases, this can lead to smaller automata or smaller transition systems with fewer states than state-based acceptance. But because these two acceptance conditions that are now here on the slide are really simple, the structure, so the transition system, gets quite big. And the goal is that we shift some of the complexity of the language that we want to describe from the transition system to the acceptance condition by increasing the acceptance condition and making it more complex. The first step in this direction is a generalized Büchi acceptance, where we require that multiple Büchi acceptance conditions need to be all satisfied in order for a run to be accepting. And if we generalize even further, we get to the Emerson-Lee acceptance conditions. And these are acceptance conditions where we take Büchi acceptance and co-Büchi acceptance as atoms and build any positive Boolean formula with such atoms. So here you can see an example where we combine two co-Büchi atoms and one Büchi atom into one more complex acceptance condition. And such acceptance conditions are really useful because one can use them to describe many other traditional acceptance conditions like Rabin or Street or parity, and many state-of-the-art tools or libraries like Spot or OWL use such acceptance conditions. So now let's look at the determinization of such Emerson-Lee automata. The traditional approach is a two-step approach where first the automaton gets transformed into an equivalent Büchi automaton. It is known that this translation involves an exponential growth of the automaton. And the second step is the determinization of this Büchi automaton. This again involves an exponential growth. So in total, we get a double exponential blow up of the original automaton. And these constructions are well known for over 30 years, so this is pretty standard. One disadvantage of this construction is that the determinization usually produces automata with a Rabin or a parity acceptance condition, and maybe we can get smaller results with fewer states if we would allow for a more general acceptance condition here. This approach is implemented in the library Spot, so it's a variant of this approach, and we will later compare our alternative approach to this implementation. So now let's look on an alternatives or a different approach on how to determinize Emerson-Lee automata. We start with the example that we have already seen a few minutes ago. The first step of the construction is to get the acceptance condition and transform it into an acceptance condition which is in D and F. So by doing this, here we get a DNF with two disjuncts. The next step is to get this DNF and look at all the different disjuncts separately. So we use the transition system once with the first disjunct and then with the second disjunct. And the idea is that we construct deterministic automata for the left and the right one separately and combine them in the end to get a result. This approach is a pretty common technique, but it wasn't really investigated how this performs for a real automata. So if we consider the left automaton and try to determinize them. This could be, for example, the result, because the automaton accepts the language where eventually no more bees are used in the infinite run. If we look at the automaton on the right, this one accepts the language where eventually the bees only occur pairwise and not single bees. And this could be, or is an deterministic automaton that accepts the same language. To get a deterministic automaton for the whole language, we use a product construction of the two automata and combine the acceptance conditions via a disjunction. So this is the result. And this leads again to a deterministic transition system, because we combined several deterministic transition systems into one, and an acceptance condition that is a big disjunction that has a similar structure than the original one. Now let's generalize from this example to the general algorithm. First, we start with a transition system and an acceptance condition in DNF. Then we split up the acceptance condition into its disjunct and determinize all the different automata, smaller automata separately. We get a number of deterministic automata, and in the end, we combine all the transition systems in a product and combine the acceptance conditions with a big disjunction. This approach also involves a double exponential growth of the automaton, because the DNF could be exponentially longer than the original acceptance condition. This is the first exponential growth, and each determinization step for the smaller automata with the smaller acceptance conditions also involve another exponential growth. So this is the algorithm to construct deterministic automata, and we can modify it very easy to construct instead limit deterministic automata. So first we need some space and shift the whole picture to the left. And this is the same construction that we have seen before. But now we don't want deterministic results, but instead limit deterministic ones. And we define a limit deterministic Emerson-Lee automata similar to a limit deterministic Büchi automata. And limit deterministic automata consist of two components. First, a non-deterministic component and a deterministic component. The runs start in the non-deterministic part of the automaton, but only the deterministic part contains accepting transitions. So every run that is accepting needs to somewhere goes to the deterministic part and stays there forever. And we can modify the construction on the left to produce such automata by simply swapping the product to a sum of automata. So instead of the product of the transition systems, we unify all the state spaces, and the result is indeed a limit deterministic Emerson-Lee automaton. The structure looks something like that. The automaton consists of n deterministic components, and the only non-determinism is the choice of the initial state, so in which deterministic component we start. And this construction leads to an exponentially larger automaton instead of a double exponential growth of the state space. So this is an easy construction on how to do this, but for our implementation, we progressed on and used more sophisticated constructions. But also this one involves only exponential growth. So in theory, it's already very good. So we have seen how to construct deterministic automata and limit deterministic automata, which can already be used for some probabilistic model checking problems. But now we are going to see how to construct more sophisticated omega automata for probabilistic model checking. The problem that we consider here is the quantitative quantitative probabilistic model checking problem for Markov decision processes. So given a Markov decision process that describes the system, and then Emerson-Lee automaton that describes the property that we are going to check, we want to calculate this value intuitively. If A is an undesired property, which is usually the case, then this value is the worst case probability that a run of the MDP or that the MDP constructs a run that satisfies this undesired property. So it's like an analysis of the worst case behavior. And the strategy, how we are going to calculate this, is we first construct a Büchi automaton B, which is good for MDP. That's how this how it's called. These automata are called. This automaton is exponentially larger than our original Emerson-Lee automaton, but later we can calculate this probability in polynomial time in the size of the MDP and the Büchi automaton B. And so in total, we get an algorithm that calculates this probability in single exponential time. So how does this automaton B look like? There are already constructions for generalized Büchi automata. So if A is a generalized Büchi automaton, then the result consists of two components. The first is a standard product construction of the automaton A. And the second one is a breakpoint construction where each state consists of two components. First, a standard product construction, and the second one is a component that tracks which of the states that are reachable in the state were reached via an accepting transition. So the second component keeps track of all the accepting transitions that we have seen in the run. And if the first and the second component matches, we reset the second component and reach such a breakpoint. We can modify this construction to suit Emerson-Lee automata by constructing one breakpoint construction for each of the disjuncts of the acceptance condition. And again, we have one initial power set construction of the automaton, and then as many breakpoint components as we have disjuncts in the DNF of the acceptance condition. And the only non-deterministic choices in these automata are the jumps from the initial component to one of the breakpoint constructions. And again, this automaton is only exponentially larger than A instead of a deterministic automaton, which would be double exponential the size. So now we have seen all the different constructions. We want to look at some experiments on how well the different constructions perform. We implemented all the different approaches using the library Spot, and for the limit deterministic automata and good for MDP automata, we used parts of the tool Seminator to construct these breakpoint components. And the benchmark that we are going to see, it consists of 1,000 random Emerson-Lee automata, which had 4 to 50 states. We display the median number of states of the output automata and the median of the length of the acceptance condition, which is the number of atoms in the acceptance condition of the output. And as you can see, our alternative determinization approach produces in general slightly smaller automata than the standard determinization approach. But the disadvantage is that the length of the acceptance condition is much larger. So this is kind of a trade-off that is always there. If one looks closer at the results, we see that the more non-deterministic choices are contained in the original automaton, and the longer the acceptance condition of the input automaton is, the better our alternative determinization performs compared to the standard determinization via a Bücher automaton. So if we look how the results look for limit deterministic and good for MDP automata, we can see that the limit deterministic automata are much smaller than all the deterministic ones, but the good for MDP automata are in general larger than the deterministic constructions. But one should note that both the two last constructions produce Bücher automata, which are automata with an acceptance condition containing only one atom. So here, really all the complexity of the language needs to be encoded in the automaton and not in the acceptance condition. And that may be a reason why these good for MDP automata are not as small as the deterministic automata. So let's summarize what we have seen. Determinization of Emerson-Lee automata is in general involves in general a double exponential growth of the size of the automata. We presented an alternative determinization approach that produces automata with fewer states, at least in our experiments. We showed that one can construct limit deterministic Emerson-Lee automata, which involves only a single exponential growth. And we showed that quantitative probabilistic MDP model checking for Emerson-Lee automata can be solved in single exponential time. Thank you for your attention. And now I'm happy to answer your questions.
Thank you for your presentation. And is there any question from audience? Feel free to ask. And you can also type in the chat. Maybe I can ask the first question. I'm wondering whether you check the time, because you mentioned here you only need the single exponential time. Did you check in the experiments?
I'm not sure what you mean with your question. So
yeah. How can you show you only need the single exponential time?
Yeah, we proved that the construction of this good for MDP automaton B is leads to an automaton that is only exponentially larger than the original automaton. And then it follows directly that the whole construction can be done in single exponential time, because for the construction of the automaton, you only need as much time as the size of the result.
Okay. Can I see the previous slide?
Yes, sure. Which one? This one?
Yes.
Or?
Yeah. I'm wondering how many of the total number of states here, because you didn't mention. Yeah, how many of total states?
So you mean how many? So the input automata had 4 to 50 states, and we gave it a median of the number of states of the output. But in general, these automata, the results can be much larger. But I'm not quite sure what you really want to know.
Okay. Yeah, I think I see. And is there any other question from other audience? Maybe a last question. Could you please go to the previous one? Also the previous one. I'm wondering, is there any?
So which slide?
Sorry, here. Is there any assumption here? I mean, for the right one.
So you mean any assumption on the breakpoint construction?
Yes.
Or? Yes, so the breakpoint construction is the one that is already described in the literature and is used for generalized Bücher automata. And we know that these breakpoint constructions are at most exponentially larger than the original automaton. So this is required that this is the case. But the construction is already known and it is proven that it's only exponentially larger. So we can assume that.
Okay, and could you please introduce, for example, some cases that could be used in your, practical case?
Yes, so if you have a system that can be modeled as an MDP, so as a Markov decision process, so a scenario where you have a system that contains probabilistic choices, but only non-deterministic choices. And at the same time, you have a property that should not be violated, for example, and you can describe this property with an Emerson-Lee automaton, then you can use these approaches to check whether or how big is the probability that runs can occur in the system that satisfy this property. And yeah, I think it's a good or it's an interesting question to ask how we can get such non-deterministic Emerson-Lee automata for given properties. So for example, if we have an LTL property, how we can construct non-deterministic Emerson-Lee automata for such a property.
Because I'm not that familiar for this part, but because you have introduced the Markov probability model, but I'm wondering whether is there any other except for Markov state.
So this is the example that we looked at here for this probabilistic model checking. But for example, the deterministic automata can be used, I guess, also for other models of probabilistic systems as well, because deterministic automata are very universal and could be used for many different applications.
Okay, thank you. And is there any other question from our audience? Feel free to ask, and you can also discuss here. Okay, if not, maybe then thank you, Tobias, for your nice presentation, and I also got some information from your slides. Thank you very much.
Thank you.
Thank you. And may I ask, is Eric
Yes.
to present the second paper?
Yes, I'm here.
Yeah, welcome. And the second paper is automatic discovery of field paths in infinite state transaction systems. And maybe, would you mind share your slide?
Yes, I'm
okay.
share them.
Yeah, I haven't seen your slide.
It looks like he has some connection issues.
Can you see them now or not yet?
I see a gray screen of
me
your
too.
browser. Ah, there we go. Okay, we can see it now.
Yeah.
Okay, just took
Maybe you can start.
Okay, already or okay, yeah. Okay, so thank you for the introduction. Today I'm going to present you the joint work with Alessandro Cimatti and Alberto Grigio about automatic discovery of fair paths in infinite state transition systems. So the problem we are dealing with is identifying whether a transition system admits at least one fair path. And this is basically because we are interested in identifying counterexamples to liveness and LTL properties. So this is a well-known undecidable problem because we are dealing with infinite state systems. And in the literature, one can find techniques geared towards proving that a language is empty, and other techniques that instead try to identify a weakness, so a fair path or a counterexample. So in such techniques, usually look only for lasso-shaped counterexamples, and of course, this is not sufficient. And we need to look for weaknesses with different shapes, so not only lasso-shaped executions. So the first issue is how do we represent weaknesses that are not lasso-shaped? So let's assume that we want to prove that this piece of code here allows at least one execution in which C is infinitely often equal to 0. So this piece of code is also represented as this transition system below. We propose to do that via a structure that we call funnel loop, which is a reachable, non-empty under approximation that admits at least one and only fair paths of our transition system. So the picture represents what this funnel loop might look like for our example. So the components we have there are basically the orange one is what we call the source region that is associated with a ranking function and a transition. So the transition here is the one that increments C. So we see in the code here that we have an inner loop in which C increments up to n. Then we reset C non-deterministically, increase n, and repeat. So in the source region, what we are doing is we are incrementing C, and there is a ranking function associated with this region that basically tells us that we will eventually reach from every state in this orange region the blue region in which the ranking function becomes its minimal element. So then eventually we reach this blue region, and from this blue region we follow this transition here marked in blue, and we increment n. So these are the transition at line 5 and 6 in our code, and we see that we set C, the next value of C to 0, while the code required only a non-deterministic assignment. So here we have an under approximation of our transition relation. So from these states, the blue transition ensures that we always reach a state in this green region that are only fair states because we set C to 0, which is our fairness condition here. Then we can see that this green region that we call destination region is fair and is also contained in our source region. So from every state in the green region, we can follow the orange transitions, basically incrementing C, performing this loop here, and again reach this blue fragment here where the ranking function is 0, and following this transition go back to fair state. So we can do this infinitely many times, and this shows that we have infinite executions that visit the fairness condition infinitely often. So basically we have our funnel loop. So this idea is similar to what has been already used and proposed for a software system, namely a closed recurrence set. But in a closed recurrence set, you just prove that software does not terminate basically by identifying a set. that is closed with respect to the transition relation. And it does not have any notion of fairness. So this is why instead we distinguish at least two different sets, one which is the source region and one destination that in this case, only one destination that must be fair. And this is how we generally we might represent infinite fair paths. So then what we do is basically we segment these infinite paths into sequences of finite paths. So basically we define a structure that we call a funnel, that is a 4-tuple built by a source region, a transition relation, a destination region, and a ranking function. So as before, we have the in the source region, while performing the transition, we keep decreasing the ranking function until it becomes 0. And in a single transition from these states where the ranking function is 0, we always reach the destination region. So basically, a funnel represents a set of finite traces that start from the source region, follow its transition relation, reaching this blue region where the ranking function is 0, and always end in the destination region. So the assumption we have on this structure is that the transition is left total, so we do not have deadlocks in this inside the funnel. And these two constraints here model what I said before. So when the ranking function is 0, we remain in the source region by decreasing the ranking function. And if the ranking function is 0, we move forward, reaching the destination region. So then what we do is basically we define a funnel loop as a concatenation of these funnels. So we define a funnel loop that represents our infinite fair paths as the concatenation of structures that represent basically sets of finite paths. This concatenation must be correct, meaning that the destination region of a funnel must always be contained in the source region of the following funnel, and the destination region of the last funnel must be contained in the source region of the first funnel. So this gives us the looping structure. Finally, this gives us infinite paths because of the loop, but we need to ensure that every such path is fair. So we require one of the destination regions to be an under approximation, so to contain only fair states. So without loss of generality, we assume this destination region to be the last one here. So now this funnel loop is the structure we want to use to represent a weakness. But how do we can we synthesize them? How can we search for such a structure given a fair transition system? So what we propose to do is to enumerate finite paths of our transition system such that we have two states that are somewhat related. So we say that there are a sequence of states that might represent some kind of loop in our system, and between these two states we have visited a fair state. So we have like a candidate sequence of states that might represent some fair loop in our structure. And then we have the stem that shows that this structure is reachable. So what do I mean by that? Is basically we consider the looping structure, and we have that we identify a candidate loop if two states basically belong to the same abstract state for some abstraction. Given this structure, we try to identify the source regions and transitions of our funnels as a strengthenings of these predicates. So it might gives us a structure like this, where the blue transitions are the transitions of our funnel. So we want this structure to under approximate our system. So every transition must under approximate the transition relation of our system. So in a bit more detail, what we propose is a procedure that, given a fair transition system, it proceeds by enumerating candidate under approximations that represent fair loops. And basically, this candidate loop is given by a witness for its reachability, that here I'm marking as V0, a sequence of regions, and a sequence of transitions. For each the candidate loop, we generate a sequence of funnel loop templates. We call them templates because we added some parametric expression, parametric predicates, and we want to identify the assignments for the parameters such that we get a funnel satisfying all the required hypotheses. So basically, we have an exist for all quantified formula where the existential quantification is over the parameters, and the for all instead is on the symbols of our system. We solve this problem trying to find an assignment. If we are able to find such an assignment for the parameters, then we found our funnel loop. Otherwise, we go back and either generate next template for this candidate loop, or we extract the next candidate loop from our model. So now I will give some more detail on how we generate these candidate loops and how these funnel loop templates are actually generated. So for the generation of abstract candidate loops, we basically rely on liveness to safety encoding for the search of fair loops, where the abstract loopback is identified by detecting whether two states satisfy the same set of predicates, so assign the same truth value to a set of predicates. In particular, we consider the predicates that we extract from the transition system itself. So then we rely on BMC, bounded model checking, to identify these paths. Then, given length k of the BMC unrolling, we extract every candidate loop of the same length of the BMC unrolling, basically by progressively adding the negation of the previous abstract, the previous candidate loop, so that in the next iteration we get a different one. So given a model identified by the BMC unrolling, we extract an under approximation of our transition system that basically corresponds to the loop that is described by the concrete model we got from the BMC unrolling. So this gives us the sequence of regions and transitions of our candidate loop. And the first thing we do is to check whether this candidate loop allows for some ranking function. So if this is the case, then the loop must eventually terminate. So the ranking function must eventually reach its minimal element. So this cannot be repeated infinitely often, and it cannot represent an infinite fair path. So if we manage to identify a ranking function, we refine our encoding, our search for these candidate loops, such that we will never generate another candidate loop that has the same ranking function. Otherwise, we extract the witness for the reachability and return this structure. Then from this structure, we generate a sequence of templates, as I said before, and this is how this is done. So we create a funnel for every region in the candidate loop. So we have a funnel loop of the same length of the candidate loop. Then we define the source region of each funnel as a strengthening of the corresponding region in the candidate loop, where we add basically a set of linear combination of parameters and the symbols of the system. So we are using linear combination, and in principle, one could use any kind of expression here. Similarly, we introduce parameters to represent the ranking function, while for the definition of the transition relation, basically we look for a deterministic functional assignment as a transition. So for every symbol, if in the transition that we have from the candidate loop, we already have a functional assignment for some symbol, then we consider that assignment. Otherwise, we generate a new parametric expression that is meant to represent how should we compute the next value for such symbol, and we consider that one instead. So finally, we define the destination region implicitly as the set of states that is reachable in one transition when the ranking function is 0. So to make things a bit clearer, here is an example of how this works. So let's assume we have two regions and two transitions in our candidate loop. So the first region, and we have two symbols, k and n. The two regions say that k greater than 0 and k less than 0. The first transition basically decreases k by n, while the second transition increases k by n. So let's assume we strengthen the regions with a single inequality. So basically, we have the first source region of the first funnel that is given by the first region of the candidate loop in conjunction with a predicate that is given by the linear combination of the symbols in our system, so k and n, with the parameters that we call lambda. So this is an affine function, so we have also a constant here, a parametric constant. And this gives us the first source region. Now, with respect to the first transition, so of the first funnel, we basically have in our transition of the candidate loop, we have a functional assignment for the next assignment of k as k minus n. So for k, we basically take that equality and use that, while there is no constraint actually on the next assignment of n. So we introduce another affine function with different parameters that gives us the next value of n. While for the ranking function, again, we introduce other parameters. Similarly, we do the same thing for the second funnel of the second region. So we have, in conjunction with parametric predicates, we have introduced other parameters for the next value of n and the ranking function. So now the goal is to find an assignment for the lambda such that this structure here represents a funnel loop. So basically, the two funnels are correctly concatenated, and the destination region of the last funnel is in the first one, and so on. So in this case, it's quite easy to see that this is a solution. So basically, the first source region requires k to be greater than 0 and n to be greater or equal than k plus 1. In this case, we have chosen to increment in the transition n by 1. The ranking function is trivial, so it's always equal to its minimal element, meaning that in a single T0 transition from S0, we always reach S1. Similarly, the ranking function of the second funnel is always its minimal element, meaning that from S1 in a single T1 transition, we go back to S0. So a bit more formally, what are the requirements we have on the synthesis of the parameters? So here I mark with P the set of the parameters in our funnel loop template. And the first constraint basically ensures that the first region is not empty. So basically, it contains the last state of our stem, meaning that is also reachable. Then we ask that if the ranking function is greater than the minimal element, then we remain in the same source region of the ith funnel, and the ranking function, its corresponding ranking function decreases. And then instead, if the ranking function is 0, we proceed and reach the source region of the next funnel. And finally, every step, every T transition of our funnels under approximates the transition relation of the original system. So this ensures that every path of our funnel loop is also a path in M. And we are guaranteed that there exists at least one path in the funnel loop, because this constraint ensures that the first source region is reachable, so it's not empty. And we defined the transitions of each funnel as left total transition relations, so they will always admit a successor. So the conjunction of these constraints ensures that I can always find a successor state that follows these transitions. So I will eventually reach a state in which the ranking function is 0 that allows me to reach the next funnel, and so on. So we implemented this in a tool that we call F3 in Python, using the PySMT library to interface with the SMT solvers MATSAT and Z3. F3 supports LTL via the usual Tableau construction, and also time system by removing the Zeno paths using the product construction with an automaton. So this is done to ensure that we look only for counterexamples in which time diverges. And we applied F3 to a number of benchmarks taken from different categories, from linear software to nonlinear software, and then LTL falsification problems on both infinite state transition system, time automata, time transition system, and hybrid systems. So this table reports the results we got. So we can see that F3 is the tool that solves most of the instances in almost any benchmark class, apart from the one of time automata, and is also the tool that solves the most instances overall. So there is a couple of things to be careful because while F3 is only capable of identifying counterexamples, most of the other tools we considered are also capable of proving such properties. In addition, with respect to UPAL, which can be used on model checker for time automata, it supports only a fragment of LTL, so we could not apply it to the whole 174 cases, but only on 116. So here in the table, we mark with a dash the cases in which the other tool could not be applied. So there are some tools that could be applied to software termination and non-termination, others on time automata, and only in UXMV we managed to apply that to every instance. So in conclusion, we have seen how fair paths can be represented via funnel loops. We have seen a procedure that reduces the search of a funnel loop to a sequence of SMT queries. And our experimental evaluations appears to highlight the fact that this approach is effective on a wide range of benchmarks. In the future, we plan to integrate our tool with techniques also to prove LTL properties, so being able not only to falsify them. And we would like to define a more incremental procedure, possibly exploiting some decomposition of the system. So this concludes my presentation, and I'm happy to take questions.
Okay, thank you for your presentation. And is there any question from audience? Feel free to ask here.
Yeah, can I ask you some question?
Sure.
Yeah, so if I understand it correctly, so this fair pass problem is somehow is a problem. To if you there's some program.
Sorry, I am afraid I didn't understand. Could you repeat, please?
It seems for fair pass problem, to non-term problem, you know.
Yeah.
Program is non-terminating. Somehow you get some, you know. So I'm wondering whether you have compared your tool with the tools that detect non-termination of programs, you know.
Oh, okay, so yeah, if you see this table here, so basically we call LS the benchmarks on linear software and NS the nonlinear ones. And if you see here, you have a number of tools that are only applied to those cases, and those are tools that try to prove a software termination. So what we did is basically took some benchmarks from the termination competition, while these nonlinear benchmarks are, most of them have been taken from the paper where this tool Anant has been presented, and we applied them to these benchmarks. So for example, ATVA is a tool for proving software termination and so on.
Okay, so this shows that the F3 performs better than the other tools that
in the benchmark
termination or non-termination of the programs.
Yeah, so these were all non-terminating instances, and also we model these softwares as transition systems. So while tools for software termination, for example, might also handle like recursion and dynamic memory allocation, we, in a transition system, we did not express those. So we consider only benchmarks with that did not use such features. So where you don't have recursion and you don't have dynamic memory allocation.
Okay, but you can deal with the integer programs, for example.
Yeah.
Okay. Okay. Thanks.
Is there any other question? Maybe I can ask in the search part, I found that you use several enumerations, and I'm wondering how about the time complexity. For example, you use some enumerations here, enumerate candidate loops, something like this. How about the time complexity?
Well, the problem is undecidable, and basically it might happen that also the SMT queries do not terminate. So from a technical level, since we can deal with unknowns, for the SMT queries, we have a timeout for every query, so that if the SMT solver does not answer within a given time, we assume an unknown answer and proceed. Then, so this is to say that the procedure might diverge. So there is no upper bound on the total execution time, and in addition, this approach is also incomplete, because, for example, we consider only affine linear function as strengthenings of our system, and there might exist no funnel built basically by adding affine linear predicates that represents the funnel for a system. And as you can see here, we also add only a finite number of such predicates. So this might also be another source of incompleteness.
Okay, thank you for your answering. And is there any other question from other audience? And you can also type in the chat. Okay, if not, maybe we can move to the third paper. Thank you for your presentation. And I think third paper is near to present the third paper.
Yes, hi.
Okay, thank you. And the third paper is certifying DFA bounds for recognition and separation. And yeah, I think you can start. Thank you.
Thank you. Hi, my name is Nir. I'm going to present a paper about certifying DFA bounds for recognition and separation. This is joint work with Ona Cooperman and Salomon Sickert in the Hebrew University. So what is the story? We ask whether, is there a deterministic finite automaton with some property? And if the answer is yes, then we can be convinced with an example. If the answer is no, then it's, well, it's not very clear how we get convinced. We know from everyday life that it's sometimes hard to get convinced that something is impossible. And our approach is to somehow show that every attempt at an example is doomed to fail. So this is the kind of the tension between NP and co-NP. So we can get convinced that the example works, or we get convinced that that there is no example. So the way we formulate this is with a game, with a two-player game. One player is going to claim that there is such an example, there is such an automaton, and the other one is going to claim that there is not. And we are going to define the game such that it is determined. So we use determinacy of games, and one of the players must have a winning strategy. So we either get convinced that there is an example, or we get convinced that there is not. So what kinds of questions are we going to analyze using this method? One is recognition. So we are given a DFA A and some number K, and we ask, is there a DFA B with K states, or K DFA for short, that recognizes the same language? So this is the well-known problem of the decision problem of minimization. The other problem is separation. We're giving two DFAs now, A1 and A2, and a number K. And we ask, is there a K DFA that separates them? So this means that it accepts all the words that A1 accepts, and it rejects all the words that A2 accepts. So we can imagine this kind of picture. So we have A1 and we have A2, and we want a separator that contains LA1, but it's disjoint from LA2. I will mention that these questions are about sizes. We have with this parameter K, limiting the number of states, but also the question of expressiveness was studied in the infinite word settings, the infinite words setting by Cooperman and Sickert in 2020. So what kind of game do we want in order to use games to study these questions? So we are going to have two players. One is called prover and the one is called refuter. Prover is the one claiming that there is a KDFA with the property, and refuter is the one claiming there is not. Prover starts by saying what is the initial state, say Q1, and refuter gives a letter, say A, and prover says, okay, my transition from Q1 when I see A is Q2, and so on. Refuter gives another letter, prover gives the next state, and refuter can also give this special symbol saying, okay, I reset and I want to give you another word, so go back to the initial state. Now, the goal of refuter is to try to expose some inconsistency that shows that whatever example prover claims to have doesn't work. It's not a valid example of the property, and prover tries for this not to happen, tries to survive. For example, here we have prover commits when Q2, in state Q2, when you see a B, you have to go to Q3. Once prover committed on this transition, she has to say the Q3 again here in order to be consistent. If she says something else, then she loses. Note that this is a safety property. So once there is an inconsistency, prover cannot win ever. So prover cannot fix a mistake. Let's see an example. So this language is A star or B star. So we start here. If we see an A, we want to continue seeing A. And if we see B, we want to continue seeing B. And if we see something else, then we go to a rejecting sync. So let's see a game here. Let's say K equals 4. So prover says there is a 4-state DFA that, that recognizes this language. And that's, of course, correct. So let's see how this works. Prover says Q1. And we see Q1 here. Refuter says, OK, I give you A now. Prover says, I go to Q2 then. So now on the right, we see what is the automaton revealed so far by the game history. So refuter can continue, give B. And now prover says, I give you Q4, and so on. This game continues forever. And there is no inconsistency because prover uses an automaton that actually works. And now we will see a more interesting example where prover fails. So yeah, suppose K is 3. Then there is not, the automaton I showed before is the minimal automaton. So when K is 3, prover is not correct. Prover is going to lose. There is no such DFA that recognizes this language. So let's see how refuter can win. Prover says Q1 like before. Refuter says A. Prover says Q2. So we have this. Refuter says B. Now Q3. And refuter says, OK, I reset. So go back to the initial state. Refuter says B. And let's say that prover says Q2 now. So we have this transition. And notice that now prover is in trouble because prover has already committed that when we are in Q2 and refuter gives B, then we go to Q3. And notice that we already know that Q3 must be rejecting. Why? Because when we saw AB before, AB is not in the language. So prover has already shown Q3 to be rejecting, but she has also committed on this transition from Q2 to Q3 when you see a B. So now if refuter gives B, then prover has to say Q3 to be consistent. But the word B is in the language. So this is an inconsistency also. So we say that this is a certificate that prover is wrong. And notice, in fact, that this was enough. This was the game history up to here is already sufficient for prover to have no good response now for the next move. So what are we asking about this game? First, let's see how many rounds does refuter need in order to win. So we're going to upper bound it. We distinguish between two refuters. Offline refuter is one that is pre-committed to the letters that it's going to give. So prover's responses don't matter now for offline refuter, while an online refuter is allowed to take the responses into account. So now suppose that N is the index of the language. So that's the number of states in the minimal DFA that recognizes it. And if K is at least N, then prover can, of course, win by using the DFA. But if K is smaller than N, refuter can win. And we have the following result. An offline refuter can win in K squared N rounds. So that's a cubic type bound. And an online refuter can win in K squared plus N rounds. So that's a quadratic type. And it is better because an online refuter can take responses into account. So it makes sense that it will be more efficient at generating the certificate. The way refuter does this is to make use of the fact that prover does not have enough states. So prover does not have enough states to accommodate more than K Myhill narrowed classes. So refuter exposes more than K Myhill narrowed classes And then prover has to assign basically one state to two different classes. And then refuter can use this to win. Prover has made a mistake, and now refuter can use distinguishing tails in order to expose the inconsistency. What about a lower bound? So we saw cubic and quadratic bounds. For a lower bound, we want to see how hard can refuter's life be. So we want an automata, a language where the DFA is, it's hard to, well, not hard, but it takes a long time to expose more Myhill node classes. So consider this automaton. We have a long prefix of A's, and then we have some letter like B1 repeated, B1, B1, or some other letter, and we have B1, B2, up to Bn. And the language is this. We have some background parameter small n, and we have A to the n and Bi repeated. The number of Myhill node classes here is 2n plus 3. And the refuter's life can be made difficult by a prover that that can adapt to the questions that refuter asks. Refuter gives a word, and every time a refuter wants to expose another state over here on the right, she has to go through this entire long prefix, like do a linear amount of work to expose just one more state. And prover, suppose that k is n minus 1, so prover is, quote, missing a state. But prover can delay this as long as possible until all of these states have been asked about on the right. And only at the last one, the mistake is revealed. So this shows that the bounds are tight. So offline refuter really does need a cubic amount, and online really does need a quadratic amount. So that's the first part of the story. The second part is separation. So let me remind you, separation, we have two automata and some bound k. And we ask, is there a KDFA that separates them as shown? So this problem is NP complete. It is in NP because we can use B as a witness, and containments can be checked in polynomial time. And it is NP hard by a reduction from a DFA identification problem, which was studied by Gold in '78. This problem asks, is there a KDFA that accepts some given set of good words and rejects some given set of bad words? The sets are finite also. So the reduction is very simple. We just construct A1 and A2 to recognize exactly these sets, and we have NP completeness. Now, we study separation and with a game, and note that now there are no Myhill node classes, so it is more relevant now to talk about the NP versus co-NP difference that I mentioned before. So the game length. How many rounds does refuter need in order to win when a refuter indeed has a winning strategy? So let N1 and N2 be the sizes of the automata. We have the following. For every K, if there is no KDFA separator, then refuter can win in this many rounds. So it's K squared sigma plus KN1 plus KN2. The strategy. The refuter will expose the DFA structure. So it will force prover to commit on all states and transitions. And now we have this property where once the DFA structure is known, we can characterize these containments with an acceptance condition, which means there is, suppose we know the DFA structure, but we don't know which states are accepting because that's not part of the game history. There is, though, a fixed subset of states that are accepting if and only if these containments hold, the one on the left. And symmetrically, there is a fixed subset of states that are rejecting if and only if these containments hold. So, okay, if we can make those that are forced to be accepting, we can make them accepting, and those that are forced to be rejecting by the other containment, if we can make them rejecting, then we would have a KDFA separator. But assuming there is not, it means that those subsets intersect. There's a state that has to be, in some sense, both accepting and rejecting, and that will be our inconsistency that refuter will expose. So refuter outputs words that force one state to be, quote, both accepting and rejecting. And we show that the words have exactly these lengths, at most these lengths, kn1 plus kn2. And the first term, the k squared sigma term, is the number of rounds that it takes to expose the DFA structure. Right. As an addition to separation, we also study strict separation. So this is very similar to separation, except the containments are now strict. So the picture is the same as before, but we want these areas to be non-empty. The outside and here the difference between B and A1 to be non-empty. So this is still an NP. We can see this just again by using a witness, and containments can be checked efficiently. It is also NP hard. So reduction is from separation that we just talked about, the non-strict separation. And the reduction is very simple. We add a new letter, say 0, to the alphabet. And this has the property that if we have a separator in the non-strict sense, and we add 0 transition from every state to the initial state, then it is still a separator like before, but this construction guarantees that there are these additional words guaranteed to be here and here, so they are not empty like we want. And we can also define a similar game for strict separation, where we would have a similar bound, similar polynomial bound for the number of steps needed for a refuter to win when there is no strict separator. Okay, so what is left to do here? I have not shown a lower bound for the separation game. We don't have one yet, only the upper bound. And another topic is the strategy size. So there is some trade-off between how complicated the refuter is in terms of if we model it as a transducer, then how big it is. There is some trade-off with that and with how quickly it can win. So there is a trade-off of strategy size and certificate length. And we have not studied this in detail. Another topic is the survival strategies for prover. So suppose prover loses, but maybe prover wants to survive as long as possible. So we can define this language. So given the automaton for the language A and a bound K and some number S, we want to say, can prover survives S rounds against every refuter? We want to classify this. And as far as I know, it is open. So let me just expand on this last point of survival strategies for prover. So one thing that is kind of the obvious question is, maybe prover can just follow the original automaton. That's what prover does when there are enough states to do it with. So when K is at least N, prover can surely win by following the automaton. Maybe following the automaton is also good when K is smaller than N. And this turns out to be non-optimal in terms of survival. So consider this automaton. So the language is this. The first letter is B, or the length of the word is exactly N. So this is here the minimal DFA for this language. We have this background parameter small n. The number of states in the automaton is n plus 3. So what refuter can do here, suppose that again that K is n minus 1, so that prover is, quote, missing a state. And suppose that prover tries to follow the automaton, even though it's missing a state, tries to follow it as long as possible. What refuter can do is give a bunch of A's. So this is the initial state. And we see A, and so on. And this makes, remember, prover is missing a state. So this exposes everything. Now prover doesn't have this extra state to get the accepting sync on the left. So this refuter can use this immediately. Once you don't have an accepting sync, it's just a couple more letters, and refuter can show the inconsistency. In this case, using BA. However, so this survives n+4 rounds. However, surviving 2 n rounds is possible with a different automaton. Prover does not follow the original one now. It follows a different one. So here is another one. There is this cycle here. So now Prover does have the accepting sync, but she doesn't have a rejecting sync. Now, of course, refuter is going to win by exposing that fact, but exposing that fact takes longer. So once we reach here, Prover creates this cycle. And this cycle is, of course, not the rejecting sync that should be there if the automaton were to recognize that language. But and refuter can show that this is not a rejecting sync by giving more letters. But in the end, this takes 2 n rounds, which is better in the general case than n+4. So for Prover to survive the maximal number of steps, it's not necessarily going to be following the original automaton, and we don't know exactly what it's going to be yet. So that is the story. Thanks for listening, and I'll be happy to take questions.
Thank you for the interesting presentation. Any question from audience? Maybe can I ask a simple question? What will happen if the refuter lose? I'm a little bit confused here.
When refuter loses, if there is no inconsistency found, so this means that, well, if we assume that refuter and prover are optimal players, then refuter losing means that prover does have a KDFA with the property that we are considering.
Okay. Would you discuss some practical use case here? Yeah, or what? Yeah.
I am not aware of applications for this. It is, as far as I know, a theoretical point of view on certifying the bounds.
Okay. And any other question from audience? Yeah, I also didn't see any types in the chat. So if not, maybe let's take a break, and later we will have a keynote. Thank you again for your interesting talk.
Thank you.
Hi, everybody. So this is the end of session 2. So thanks very much for all the speakers for all those fantastic talk. And now we're going to have a 30 minutes break. And during the break, there's an announcement. So let me introduce Zhiling Wu to you. So he will be one of the PC co-chairs of the next year's conference, ATVA 2022. And he will give you some more information of the conference next year, as well as how ATV will go in the future.
Okay, thanks, Joe, for introduction. I now share the screen, right? Yes, let me see. Share. Yes. Can you? Hey, screen now?
Yeah, I can see.
Yes,
it.
yes.
Okay, thanks. So, I'm Zhening Wu from Institute of Software, Chinese Academy of Sciences. So, good afternoon, or good morning, or even good night to everybody here. So 2022 will be in Beijing, China. Hopefully, we will have a offline conference, but we will see. Okay. As I said, we are expecting a hybrid conference combining online and offline activities. So let me talk about a bit more about the ATVA next year. So for the dates, the abstract submission will be April 20, and then paper submission will be May 1st. Somehow following the tradition of ATVA, this paper submission deadline is just after the notification conference. Okay, and then the notification deadline will be June 17th, and the community will be July 15th. The conference will be October 25 to 28. Okay, so this is the dates. So as I mentioned, this conference will be in Beijing. Beijing is a big city, and with a known history, it is famous for Forbidden City, Great Wall, and also Summer Palace, and many other tourist places. So it's if you can come, I think you will enjoy Beijing. We will see. More precisely, the conference will be in the Institute of Software Chinese Academy of Sciences, abbreviated as ISCAS. So ISCAS is located in an area called the Haidian District, and this district is famous for higher education. For example, the Beijing University and Tsinghua University are in Haidian District, as not it's close to Institute of Software Chinese Academy of Sciences. Moreover, Summer Palace is not far away from ISCAS. So if you can come and attend the conference, actually it's very convenient for you to visit the Summer Palace. Okay, so to give you more idea about where the Institute of Software Chinese Academy of Sciences is located in. So can be reached from Beijing Capital International Airport easily by public transportation. For example, by airport shuttles or by subways. And also, if you take a taxi, it will take you around 36 minutes from Beijing Capital International Airport to ISCAS, and the distance is around 30 kilometers. Okay, this is the place. ATVA 2022 will be held. Then let's see more information about the organizing committee. So general chair is Hui Minlin from ISCAS. There are 3 PC co-chairs. I'm Deb Jenny from University of Paris, France. From Bordeaux Institute of Technology in CZEC. So myself from ISCAS. Local organization chair will be Rong Jieyan from our institute. Okay. So we have consolidated our programming committee consisting of 42 PC members, and these PC members are geographically balanced. So 18 of them are from Asia or Oceania, and then 17 of them are from Europe, and 7 are from America. Okay. So here are a list of the program committee members. You can briefly browse them here, but I will not go into the details. Okay. So then there are 5 keynote speakers. So Mohammed Fauzi Atike from Uppsala University, Sweden, and Xu Feng from Nanjing University, China, and Shaz Kadir from Facebook USA, and also Jean-François Raskin from University Neighborhood Bruxelles, Belgium, and Sanjit Seisha from University of California, Berkeley, USA. They are world famous researchers in former methods and related areas. Okay. Moreover, they also have there will be also 2 tutorials by Constantin Allais from Nix École Polytechnique, France, and also Visvala San from you. So these are the tutorials. So for the accommodation, have chosen 2 hotels close to our institute. So the first one hotel is the Park Plaza. So it has single train rooms. The price will be around 6. The
Hi, Julie. I think there might be some internet issues. We can see your slides, but we can't hear you. Any questions from the audience? I believe it's going to be a fantastic conference next year. So really looking forward to it. Okay, thanks, Julie, for presenting the overview of the conference next year. So let's now have a break, about half an hour break. So we'll come back at 5:30 in Brisbane time, basically in half an hour time. And we'll have the first keynote. Now, the first keynote is supposed to be given by Tony. but unfortunately, as I mentioned this morning, so Tony Hall is currently ill, so he cannot present the talk live today. And he asked me to give the keynote on his behalf. And so I'll be honored to do it. And if you guys have any questions regarding the keynote, and ask me if I can answer, I'll answer that. If I cannot, then I will relay your messages to Tony. Okay, so we'll see each other in about 25 minutes.